re-energized, and it's my pleasure to introduce our next speaker, Mike Kraus, and he is going to tell us something about, what I understood, kind of the comparison between Python and Rust and the performance. So I'm looking forward to this. Give it up for Mike.
Thank you. Good afternoon, everyone. As mentioned, my name is Mike, and I'm a machine learning engineer at Molly. For those of you who are not familiar with Molly, Molly is an all-in-one platform that at its core enables businesses to accept payments, both in an online setting and in a point-of-sale setting. So whenever you make a purchase in the Netherlands, or in a web shop based out of the Netherlands, there's a pretty good chance that you'll see us pop by on your bank statement. Now you also probably understand why I'm a bit uncomfortable here today, because on the one hand I'm in front of this audience, but on the other hand I'm also wearing this Adyen branded thing. So my body opposes that a bit, but I'm good to go. I'm good. So if you see me like sweating a bit, that's this thing. That's not the presentation, if you wonder. All right. So I'm a member of the MLE team. Together with my fellow MLEs, I'm responsible for maintaining the machine learning platform and enhancing it, and also bringing data science proof of concepts to production. And what I've noticed over those couple of years that I've been at Molly is that there are a number of packages that slowly have been creeping into our repo that use Rust under the hood to boost performance. For instance, I attended a talk of Polars yesterday. Well, Polars does exactly this, right? You talk to it via Python, and under the hood, it reaches out to Rust for performance purposes. You probably also know PyData for data validation purposes and serialization purposes. We also now have Rough coming in to challenge Pylint and Flake 8. So there are more and more packages coming in, and that raised a question on my end, like, okay, if this is all happening, can we do the same thing with custom code that I have in my repo? Because not everything can be addressed with a package. And that's the question that I'm going to try to answer throughout this presentation. And of course, what would it take? And would it be worth the hassle, or shouldn't we even think about it in comparison to all the other methodologies that are out there that you can use to speed up your performance? Or is this just a hype, right? It can also be a hype. So especially this latter question, I thought, before I dive into it, let's just first have a look and see where it stands, this particular language. And I took out the most recent developer survey from Stack Overflow. Yes, they still exist. I was amazed as well. And what they did, they went out to developers and they asked them this question like, hey, what have you been using last year in terms of languages, and what will you be continuing to use next year? And they call this the desired languages, if you like. And which language do you really want to work with next year? And as you can see, Rust stands out quite a bit, right? Adoption, like the blue stuff, the desired stuff, it's pretty on the low end. But on the admired side, the people that really want to work with it, it's out of the charts, basically. So you could say that practical use is still on the low side, but there are a lot of people out there that want to use it. And maybe, just maybe, my talk will move some people to the blue side. Depends, of course, on the conclusions that I got in store for you, right? So I went into these two questions that I just mentioned, right? It's a bit of a fact-finding mission for me, to be honest. Like, I'm from the Python side, originally data scientist or machine learning engineer, and I just jump into this thing. So it's a fact-finding mission of a non-Rust expert, if you like. So what I'm going to do today, I don't have an agenda, but on a high level, I'm first going to talk a bit about Python, about why it is as it is, and after that, I'm going to move to Rust, where it stands out, what it does. And then I'm going to go through a little practical example that I cooked up, just to see, like, okay, what does it take in practice to do this particular trick that Pydantic and the Polars are also doing. So I'm going to start off with Python. I don't need to explain to any of you that it's known for its simplicity and flexibility, right? There's a vibrant community, tons of packages, and in my opinion, you don't need to worry about anything with Python, right? You can just go off, do your thing, create a script, prototype very fast, nothing to worry about. But this comes at a cost. and that is performance, obviously. Now, where do these costs come from? First of all, it has to do with Python's interpreted nature. So under the hood, Python objects are C structures. And if you're running a script, the first thing that happens is that it gets transformed or compiled into bytecode, and the interpreter then starts interpreting all the stuff you wrote. That's overhead, basically. So that's one of the components we get out there. And dynamic typing actually ties into this interpreted thing. So this is the thing that we, as MLEs and data scientists, always work on, right? To type our variables. We use typing, we use pydantic, all that stuff. But under the hood, it still is going to try to infer a particular type. So you can all just put your types in there, but still there's this overhead that needs to be done at the point of interpretation. Now, there are also a couple other components that lead to this particular cost. Does anyone has an idea where this might come from? Yes, that's one. Good stuff, good stuff. I'm going to get to that one. First of all, memory management. So in the back of Python, you have this global garbage collector that runs, and that basically keeps track of all the references to objects out there. And whenever a reference to an object reaches 0, it removes it from the memory. And all this stuff takes time. It takes overhead. So that also adds on top of this. And of course, as you just mentioned, the global interpreter lock. So in order to facilitate all this stuff, all these items above, it was decided to introduce this global interpreter lock. And what it basically does, it restricts everything. It says, hey, whenever you want to run a Python process or run stuff in your interpreter, you can only use one core at a time, one single thread, and that's it. So it's basically blocking you from your from getting to performance, right? In the perfect world, you also want to do stuff concurrent. Now, there are all kinds of alternatives to that, depending on whether your problem is input or output bound, or whether it's compute bound. But I'm not going to talk about that. It's just going to be about Rust today, and how we can make that bridge from Rust to Python, and whether it's worth it. So, where does Rust come in? Well, it is set for people who want speed and stability, but don't want to deal with all kinds of nitty-gritty stuff. A good example is C. If you want to program stuff in C, you also need to do all your memory management manually. That's a lot of hassle, especially when you don't do it right. Your programs can really turn into unstable monsters. And this is one of those things that the creator of Rust tried to address. So this is one of those things. It is perceived to be quite a bit harder than Python, and I can personally attest to that. That has been quite well. You have to really dig into it, so you have to invest in it. Now, speed and stability without nitty and gritty stuff. So where are these components then in this particular language? Now, first of all, and this is not unique to Rust, it's a compiled language. So every time when you want to run some code, you first need to compile it, which basically means it's going to turn into machine code, wrapped into a binary, and you can then execute that binary. The nice thing about this is that you don't need to install anything on your computer, right? You can just give the binary to someone, and provided that it's compiled for the right architecture, you're good to go. Now, in this compilation process, a lot of stuff is happening. And when it comes to Rust, that means quite a number of optimizations. So, for instance, if you have a lot of for loops in your code, it's going to automatically vectorize that stuff. Also, it's statically typed. That's not unique to the language, but it does mean you need to type all your stuff before you want to go. So it's going to be a lot of back and forth between the compiler. Good thing is that at runtime, there's no inference taking place anymore, right? So no more overhead. But again, not unique. What is unique, that's memory management. So instead of this garbage collector that I just mentioned, you don't have this anymore at Rust. There are simple, transparent rules that deal with memory management and ownership. So that also means that, like I just illustrated with C, that you don't have to do all this manual stuff anymore. You don't need to worry about it. You still need to worry about it to a certain extent. So you need to understand the concepts of ownership within Rust, but you don't need to go like, oh shit, I have this C struct over here. How do I release it from memory? And is this the right moment? Blah, blah, blah. You can forget about that. That helps. Now, this stuff, like especially this previous bullet, that's facilitating concurrency. So you don't need to worry anymore about ownership and data races, dangling references, all that stuff. So when two threads are trying to access an object at the same point in time, that stuff you don't need to worry about it anymore. So concurrency is really like one of its strengths. Also, because there's no garbage collector and there's like these transparent rules, you don't need to, you can actually easily go from another language to this language, right? So you have this foreign, they call that foreign function interfacing from other languages, make that bridge to Rust, use it for its performance, and go back. It also comes with a couple of zero-cost abstractions, or high-level abstractions. I'm going to get to that in a minute. And this last point, and this is not a sales pitch for Rust, because I'm going to get to the points where it's really shitty, actually. There's one unified way of creating, building, documenting, and testing projects. Nothing to do with the execution of your code. It has to do with the way you develop your code. In Python, we have Conda, we have Poetry, Vent, PyEnv, PipTools, you name it. Over here, you can use Cargo, at least for now, and that does the trick for you. Any drawbacks? Yeah, a couple. I'll get to those in a bit. So I just want to dive into this ownership model before I move on to this practical, like this dummy case that I worked out. So memory management is done through these ownership rules, right? And these are enforced at compile time, right? At every point you want to compile your stuff, it basically says to you, hey man, this is what you're doing, that's complete shit, that doesn't work. And it's very verbose, it's very explicit. Can be a bit annoying, of course, but that's with every language. So one example of those ownership rules is that you have to think in scopes. So everything within the curly brackets you see here is a scope. And whenever a variable is in this particular scope, and you go outside of the scope, for instance, the outside bracket, it's going to be removed from memory. That's an automatic rule. This is one of those things that you have to keep in mind. So developing requires you to think in scopes, and it requires you to think in ownership. And in Rust, one of those rules is like every object has a single owner at any given time. That's quite a bit different from Python, because in Python, variables are references to objects. And when you assign one variable to another, both variables refer to the same object. So in the end, what you're going to have is like multiple owners of a certain object, which even in a single-threaded setting can be quite painful, let alone in a multi-threaded setting. I got an example of that. So let's say that we have a list, S1 here, with 3 integers in it, and we assign S2 to S1. Now, if we modify that list, that's going to mean that both S1 and S2, which are references to this list, are going to reflect the exact same thing. So multiple owners. And you've probably seen it with pandas as well, right? The copy, you don't forget to copy, because otherwise you'll see it all over the place. Okay, so I can talk about those ownership rules for hours on, but I'm not going to do that. That's going to be quite boring, especially on a Friday afternoon. But those rules make it that concurrency is one of the strengths of Rust. It's ownership system, and in a way, it looks a bit like Python if you actually try to put it together. So I've put some code over here, which spawns up 5 threads, and it waits for 5 seconds, and then brings it all together. It looks quite a bit like multiprocessing. I'm not sure if anyone have used that module before. It's the same thing, but if you look under the hood, what you're going to get is 5 different Python processes running at the same time, each using their own single core that they have. And those processes also need to talk to each other. So you have data serialization going on back and forth. Painful, quite painful. But then again, you have your flexibility, right? So you choose your language for whatever purpose that you need. Then let's go to the abstractions. So there are high-level abstractions in Rust, and you've probably seen them in Python as well. Iterators, closures, and they don't introduce any overhead in comparison to other languages, like Python. So for instance, if we have this stuff here, this is Rust, a vector with 5 integers, and I want to iterate over it, I want to filter the even numbers, double them, and then sum them up. Well, you only need those 4 lines. But you've seen that in Python as well. This is nothing new. The only thing is that with Python's built-in abstractions, they are powerful, but they're definitely not zero cost. These are more like things that later on were like appended to the language, while with Rust, it's really baked in there. So this is as fast as writing out this for loop and doing all this stuff. Well, in Python, that's not the case. So you could better write out your for loop and all that stuff. All right, so connecting both worlds. So we have Rust for high performance, memory safety, and concurrency. And we have Python coming in when it comes to ease of use and rapid development. So let's use those languages where they stand out. So how can you do that? What you could do is you could say like, hey, I have this Rust kind of setup, and I'm going to compile it into a binary, and it's like a CLI then, and then I'm going to do Python subprocess and reach out to it. It's one way of doing it, but it's not overly elegant. So there are a couple of packages out there, and I think PyO3 is the most popular one, which comes with bindings. And those bindings allow you to bind Rust objects to Python objects. But those are only the bindings, right? So you expose Rust stuff via those objects to Python. Only the bindings. But with only the bindings, you're not going to get there. So you need something to actually build it into a Python package that in turn reaches out under the hood to Rust to do its trick. And that's where a Maturin comes in. I looked it up where they found how they came up with this name. It has to do with a turtle, I believe. And this turtle is like the main character in there was in Stephen King's novels. There was a turtle which created the whole multiverse. So now you know. It's quality information, right? Let me see. So you have those two packages, right? And those are the two you're going to use to get to this bridge. So breaking it down, how is it going to look like? First of all, we're going to initiate the project. And what you're going to get is this particular setup. So we have a cargo.toml. That's for your Rust code, right? Your dependencies will all be there. You have your source folder with lib.rs. That's where your bindings are going to reside. And on top, you have a pyproject.toml for the Python world. And for instance, you can put your whole script into this file over here. And that one is going to import your package and call it. You can put it all in all kinds of other ways as well, but this is one way to do it. So Python and Rust. So you write your Rust code using PyO3 to define functions, structs that you want to expose to Python. You use Maturin to build your project, and this will compile the Rust code into a shared wheel that you can then, in turn, install in your environment and import as any other Python package that you can use. All right. First, I'm getting a dry mouth, man. Sorry. All right, so now let's get to practice. So I work at Molly, and that's all payments. So I thought, why not create a little Molly world with a lot of compute shit going on? So we're really going to turn it on, because compute is the problem here that we're trying to solve. And we're first going to create like our Python setup, and then we're going to try to create those bindings, compile it, and see how it stacks up. A payment handler. And what it does, we're going to shoot a lot of payments to this payment handler, and it's going to update balances of our clients. And clients in our world are then, let's say, a web shop. So we're going to shoot payments, and we're going to handle those payments. We're going to update balances, and we're also going to calculate a set of statistics periodically, because updating balances, that's like already quite efficient in terms of compute. So let's also shoot some other stuff at it. So we're going to calculate a set of statistics periodically. And more specifically, I'm going to initiate the customer's balance. I'm going to also initiate a payment count and set it at 0. And I'm going to process payments as they come in, add it to the history of a consumer, add it to the payment count, update the balance, add it to a historic balances collection, then calculate the moving average and moving standard deviation over the last X payments over a window of X. And I'm also going to add a little risk management metric in there. So we're also going to calculate the value at risk for the balances that we see come in. So what we're going to do there in this calculation is like, look at all the balances, take the 95th percentile, and then we know, like, if the world is normally distributed, that 95 out of 100 times we will not go below this particular balance, which is kind of a risk indicator for us. So a lot of stuff happening at the same time. Would we ever do it like this at Molly? No, this is just a dummy project on the side. So just to test out this hypothetical case, right? That's what we're trying to do here. And we stick to CPU bound, so pure compute, as I mentioned, and single-threaded, because we're competing with Python for now in its base setting, just only one single thread. And then in terms of parameters, I'm gonna send it some stuff. Let's say that we have 3,000 customers, we have 10,000 payments per customer, so in total we have 30 million payments. They can be positive or negative, and they're 80% of the time positive. We shuffle them, and we have every 100 transactions, we calculate those statistics over the last 100 transactions. So that's going to be a lot of calculations. Same applies to, yes, same applies to the 100 transactions. The historic value at risk. We're going to do that as well, every 100 transactions. But then over the entire history is also compute heavy. And we're not going to cheat here. So no NumPy, no pandas, no polars. We leave it to the just standard Python to do the heavy lifting. And we start profiling from the point where we're processing payments. And we do it on this little beauty over here, 8 cores, but effectively we're using 1 core, right? At least with this example. And for now, I opted just 20 runs. We don't want to burn this thing up. You know, Molly will not be happy with that. Okay, so starting with the essentials, and I'm going to share with you the repo afterwards, but I'm going to go through a couple highlights in this particular repo just to show you how we're doing it. So we have a simple class, payment handler. We initiate payments, payment counts, current balances, historic balances. Those are dictionaries, and in those dictionaries we have lists, and lists are horrible objects in Python, right? Because there's a lot of overhead coming in there. And we process a payment, so whenever we come in, we initialize a balance if it's not there. We then append it to the payments collection. We up the payment count, add it to the balances, and append it to historic balances. So nothing funky going on in terms of code. There's more to it, but I'm going to just go through the highlights. Then the metrics, so the value at risk. As I said, we're going to get our balances in, and we're going to sort them all from high to low, and then take the 95th percentile of this thing, or the 95th index value, and that's our value at risk. Standard deviation, I'm not using any kind of other packages outside of the standard stuff we got. So yeah, we're going to calculate standard deviation. First, we're going to get to variance, and then get to standard deviation. That's Python. So what does that look like if we just shoot all these transactions at this thing? So on the left, we have here, in total, we have 20 runs. And over here, on the x-axis, you'll see how long it takes. And on average, we got 2.5 minutes, something like that it takes to go through this stuff that we set up. But now comes the interesting stuff. Let's convert this stuff to handler. And to Rust, sorry. Let's convert it to Rust. Now in Rust, there are no classes. So you need to do something else there. There's also no inheritance. So you also need to think about something else there to really fix it. So what you can do is you can use structs and implement blocks. Structs are your object to define custom data types. And the implement blocks, they actually allow you to create methods on your struct. And we're going to use hash maps. A lot of hash maps basically coming in. Those are like your Python dictionaries. They use the same kind of hashing methodology for index values. Same stuff in a way. But it looks a bit different. So let's say that we go to our class. It's now a struct, right? A payment handler. And we have our payments, our payment counts, our collections. Those are hash maps. And we have this little macro attribute from PyO3 coming in that exposes structs as classes to Python. And this is solely made for structs. So you can't do this with anything else. And that's also one of the drawbacks that I'll show you in a bit. So we have our payment handler, and we're going to expose it as a class. Now we also want to have a couple of methods. Like we want to instantiate our payment handler, right? Stuff needs to be instantiated. And that same applies to all this functionality that I just showed you. Well, there's another attribute called PyMethods. You have to put those around your implement blocks. These are like, call them Python decorators 2.0, a bit more flexible. So that's like your base case. And then getting to your statistics. Well, when it comes to your standard deviation, it now looks a bit different, because what you see here is now that your values are my balance values coming in. We iterate over them, we reverse them, we take the first 100, and then we have this closure coming in that takes the difference between the balance value and the average, and then to the power of 2. And these are those zero-cost abstractions coming in. So I forgot that, by the way, my performance slide. There are a couple things. I've also profiled it, where you can see, like, hey, where does it really take a long time? When it comes to payments processing, just appending to dictionaries, pretty fast. But when it comes to metric calculation, it lags, actually. And this is where Rust also stands out. Same happens when you calculate the value at risk, right? We also sort our values, and we use this closure over here to do that trick. So, okay, I'm not going to go further into detail of the code. You're going to have to look at the repo yourself after this talk. But it's like the high-level picture is there. The next thing you need to do is say, hey, I got my payment handler struct, and I want to actually add it to a Python module. And that's where this particular Python Rust macro attribute comes in. Also from PyO3. And that's it. And then the next step we need to do, we need to build our package, right? And then we use our build manager, Matcherin, to do the whole trick. Important though, that whenever you do that, you want to do it on the release mode, because otherwise there will be no optimizations taking place. You're going to do it in dev mode, and it's going to be a bit sluggish. And you want to make sure that you put it for the right architecture type. That was quite a struggle on my laptop, actually. So we have it. Now I go back to my Python world, and I import my, I've installed it, right? I've also installed it. I'm going to my payment handler, import it, and go through my payments. And this is what you get. So this is the happy flow, right? Things are still going pretty okay. Minus 30%, which looks pretty okay, I would say. But let's push it a bit. Let's say that we actually want to use concurrency, because that's what Rust also is strong in, right? So what you can do there is you can use this crate called Rayon that assists you with doing parallelism in your code. And what I can do is I can actually go through all my payments, iterate over them, and create a thread for each payment, and off you go. Is this like the real world? Nah, not really, because no one's going to send 30 payments just all at once to us. So the results are a bit overstated, but it gives you a bit of an idea what you can do. Now, all those collections, they need to be made thread safe. So what we need to do is put some mutex around it, and we want to make it some shared ownership, so that separate threads can actually write to that collection. But we made a couple assumptions there. So we assume that all these payments are a bit distributed across all the merchants out there. So if you have all these merchants, like merchant A or webshop A, and then another webshop A, that's going to be messy, because they're all going to be competing to get this lock. So we assume that it's all a bit distributed. But it's still a bit overstated, because from the Python world, I'm not doing anything concurrently. I'm just sending it all the payments all at once. So the results are a bit overstated, but in orange over here on the left, that's like your concurrent mode of doing this particular trick. So we go down from, what is it, 2.5 minutes to 1 minute plus 67 seconds, so minus 55%. Now, that was all the happy flow so far. So a couple observations. Oh, yeah. So we use Rust in areas where it stands out, but performance fluctuates with input. So if I send it 30 million payments, it's going to work out well, because that's a lot of stuff, right? And the overhead of translating is relatively low when you send out the whole bulk. But if I'm going to send it just 10 payments or 20 payments, then your whole performance gain is almost gone, because there's also a translation cost between Python and Rust. So only when you have like large amounts of data coming in, then this is something you could do. And all those gains, they're confined to a couple of calls, right? Specifically in the metrics section, because all that stuff like appending to dictionaries and that's all optimized in C already. So there are not a lot of gains there. A bit, but not a lot. Parallelization gains, those are no surprise. But when you're developing this stuff, you don't have a REPL, you don't have a terminal. So it can be quite painful to prototype this stuff. It's back and forth, compile, back and forth. So to that extent, I was happy to have Copilot sitting next to me. I'm going to be honest with you. So you need to dig into the language, but you also need a nice assistant to help you along. But you don't have it, right? And that's something that, that's Rust, right? No immediate response on your code. You need to invest, right? You need to invest in the language to understand it, and it increases your complexity of your dev setup. And last but not least, if you use non-Python standard libraries, like any other library with a custom object, then Rust doesn't know what to do with it. So you really need to create your own kind of PyO3 binding to work with it in the Rust world. So as long as everything is standard, then you're good to go. Gains are there, but are they worth it? Well, Python and Rust both have strengths and weaknesses. And if you use their strengths, you definitely have a strong combo. But bridging from Python to Rust is no silver bullet, I learned. The low-hanging fruit, if you ask me personally, and I'm sorry, but most likely to be found in other areas. So for instance, like the first thing I would do is like, okay, just sleep at night, and then go back into your code, see what you're doing. Oh, you're using lists there in your dictionary. Or maybe I should use a NumPy array or something else to speed it up, right? So often going back to your code is also very handy. Of course, specific tooling that uses the strengths of other languages, like NumPy, Pandas, Polars, you name it. Or concurrency in Python, right? But then the input-output bound concurrency, use async IO, right? To efficiently work with your single thread. Just-in-time compilers, or even go distributed computing. So there are a lot of flavors out there. This one, is okay, but I wouldn't really use that like the first one on my list to speed up my code. That's my talk, actually. So this is the repo. have a look, I would say. Yeah, thank you. Have a great weekend. Good time.
All right. Thank you so much, Mike. Are there any questions for Mike? Yeah, I see a hand there.
Thanks, Mike. You mentioned zero-cost abstractions a couple of times, and it might be because I'm tired, but I don't get what zero cost. What's zero cost?
Yeah, so normally, let's say that you have in Python, you have an iterator, right? It goes over things. It still has this little state kind of variable in between there that needs to keep track of state of where it is. So eventually, you rather would like to write out your code, right, in terms of for loops or something, and that would be more efficient than this iterator, which was added to the back later on. And when it comes to Rust, there's, as far as I'm aware, there's no difference between both sides. So you have, like on the one hand, you have your iterators, and you have you make it explicit, and they're both as efficient. So I'm not talking about the Python overhead, right, that you, from an interpretation point of view, already have. It's just between those little things, like using the built-in iterators of Python. Yeah.
Right. Other questions? Yeah. Mike. Do you have a mic? No.
Yeah, thank you. In the back here. So your use case is like Python only, and in my view, you could go JIT on that with what is PyPy or Numba. And PyPy seemed to have worked on all these integrations with like non-standard built-in libraries. What's your take on that, in the sense that that might actually speed up? And currently also CPython is not really aiming at more features, but at improvements like speed.
Yeah.
So what's your take on actually, maybe we can even rely on CPython for a lot of stuff, and it's not as slow as it used to be.
Yeah, no, I completely agree with you. So yeah, that's why I'm also not seeing this as like the solution you should try out first, especially when it comes to numerical compute issues. Then I would definitely not go this route, to be honest. I would really go more like your route, for instance, with I never use just-in-time compilation, but there are multiple things that are way easier to use. Like I would, for instance, instantly get out polars, right? If we're talking about tabular data and we want to do transformations, like hell no, I'm not going to go create my own stuff. It's really like more for custom kind of use cases where you don't see any packages out there. And maybe if you want to package something, then you know, like, hey, if I want to do it in Rust, then you know this is the way to do it.
All right, thanks.
Other questions? You're over here? Yeah.
So a bit of a continuation of a previous question. Do you have real use cases in your work? Because
good question.
most of the time I'm trying to think about it. So
yeah.
99% are covered by polars or some other stuff, and
you're right.
I can't think about like when I would like to write Rust.
You're right. Yeah, you're completely right. So for me, it was more like a hobby project that, like, got a bit crazy. But you're right that if you look at our use case within the data science domain, I don't see any kind of application straight away because there's so many good packages out there. So yeah, fair point.
Thank you.
There was a question at the back.
Go back one slide. That's it. People wanted to take a photo.
Oh, sure.
Right. There was a question at the front here, or did you have the same question? All right. Yeah, one more question.
Instead of combining Python and Rust, could you see just a total migration to Rust, or how do you see that in comparison to doing this integration?
Now, if you just talk about like in the area that I work in, machine learning or Python, no. Definitely not. Like there's so many dependencies we got into our projects, right? That do all these nifty tricks when it comes to training models and deploying models. I don't think it's going to take quite a bit to do a full migration to Rust. Although it is like the community is getting bigger. I noticed like there are a lot of crates out there that do a lot of interesting stuff. But like at this point in time, I don't yet see it. So you really have to rely on people doing the Rust bridge for you in their packages, in their Python packages. Yeah.
Thanks.
All right, final question.
Do you have any experience with, if I don't want to write Rust, but perhaps go with a faster language like Go, do you have experience and ideas how this performs out and if this is possible?
I can't answer that question, I'm going to be honest with you.
Okay.
No, I never coded in Go. I did make a bit of a selection though when I was working in Python. I thought, okay, which other language would be the next best thing or the most valuable for me? Then for me, Rust stood out, right? Because it's comparison to C, it's like a different world. In terms of Go, yeah, I don't know. I don't know, to be honest. Yeah.
Okay, let's give it up one more time for Mike. Thank you so much.
Thank you.